Okay, what did we cover in the last session? We covered SLL, singly linked list, and CLL, circularly linked list. You can see CSLL, circularly singly linked list. And why did we define CLL? The reason we define CLL is because in some applications, we might encounter processing of the elements in a round robin fashion, right? In a circular fashion. Then it would be better to use CLL. And CLL, as discussed in the last session, does not asymptotically improve on SLL, right? But it cuts down a lot of computations and there is a practical impact, right, on the performance. Yeah, so we covered SLL, we covered CLL, and we still need to cover DLL, doubly linked list, and we still have to look at dynamic arrays that we will see next. Okay, we will cover doubly linked list and then we will cover dynamic arrays. We just looked at static arrays. What are dynamic arrays? How are they different from static arrays, right? So we will cover all this. So let's go back. So we just defined what is a doubly linked list. It is like SLL, now just that every node has a pointer to its previous node, right? So you have a previous pointer as well, along with the next pointer. Okay. And we also said that the way we will implement DLL will be slightly different from the way we implemented SLL, because we will use header node and a trailer node. And this is a different concept from the head node and the tail node. Head included data, right? The tail node included the data in SLL. But here in doubly linked list, we have created two sentinel nodes. These are called sentinel nodes because they don't have any data. They don't store any kind of information. They are just there for comparing with or checking whether you are inside the list or you have encountered the end of the list, either end, left end or right end. Okay, header node and trailer node. And why did we define it? The beauty of this implementation compared to many other implementations is that we can handle inserting a node and deleting a node in a unified fashion. What do you mean by a unified fashion? So we just need to define two functions. One is insert between and another function is remove node. Okay, what is insert between? You are given two consecutive nodes. You want to insert a node between those two consecutive nodes, that is insert between, and then remove a node. Okay, so using this insert between, you can easily construct insert at first position, insert at last position, right, and insert at any specified position. And similarly, using remove node, you can implement remove at first position, remove at last position very easily, just calling this unified function. Okay, we will see how. So we discussed the core ideas before. We will not go over it. Okay, let's look at the implementation. As before, I mean, this is very similar to your SLL implementation, just that you have sentinel nodes, right, header and trailer, and then you need to take care of previous pointers. That's it, right? Currently, you had to worry just about the next pointers in SLL, but now you need to adjust and fix all the previous pointers as well. And if you compare, see, we had difficulty in improving remove last in SLL. Why was that? Because removing a node from the last position, we had to scan the entire list and it was damn slow, right? Add first was O of 1 time, add last was O of 1 time if we had a tail pointer, remove first was O of 1 time, but remove last was O of n time, or you can say theta of n time in SLN. But now you will see that remove last can be implemented in DLL, and that takes O of 1 time. That's it. Okay, so we can implement all these functions in constant time. Constant time means theta 1 or O of 1. Okay, so here is our class DLL, right? And it has a node. Let me annotate here. It has a private node, right, as before, right? And then we have two sentinel nodes, right? Header and trailer. And of course, we should always keep the size of the data structure. For any data structure, we will also have that size, the number of elements, size, number of elements. And then we have access methods and update methods. Access methods are just to get information. This is to get information. And update is, you can say, setting the data structure, set some information, right? Setting the data structure. Okay, so getting is, okay, this is just a constructor, doubly linked list, and then size, get the number of elements, is empty, simple, get the first element, last element, simple. Okay, these are the functions we really want to implement. Okay, so to implement this, so I said that we will include some, okay, unified functions, right? What are those unified functions? There are a lot of windows here. Okay, so one is add between and remove node, just remove, right? So these are unified functions. These are private functions. They are not available for a programmer directly, right? See, these are private methods. So understand the difference between private methods and public methods. Public methods can be accessed from this object, right? From a main function or something like that. So you can directly call all these functions and change the data structure. What about these unified functions? These unified functions are not available to be directly called publicly. They are private functions. So that means they are used as intermediate functions, right? To solve the problem efficiently or to solve it in a modular way, generic way, but these are not available for the programmer directly. Okay, so you cannot call these
Hey, Professor.
From the main function. Yes.
Sometimes your voice is broken up. I don't know if it's my issue or your issue.
What about others? Is it the same problem?
I'm not having a problem.
Me neither.
Okay, so maybe it is the
Okay.
internet issue, I think, right?
Okay, thank you.
Okay, so we will use this private update methods, unified methods, and implement all these 4 functions. Okay, let's see how.
Professor, can I ask a question before you go on?
Yes, yes.
So you have the node class as nested in here for encapsulation reasons. But if you made that its own class and its own Java file and made it private, would that accomplish the same thing, or do you need to have it nested for the encapsulation?
I'm not exactly sure whether you can implement it in that way, but if you have it as private, it should work. But I'm not sure about
If you
the
make
feature
it
you're
a
talking
private
about.
class. Yeah, I was just wondering if you made it, because when I learned this, we made them private classes.
Mhm.
I'd have to go back and look, and I just wasn't sure if that would accomplish the same thing. But you know, maybe I'll just
Yeah,
write
so
it and fool around with it.
yeah, I'm not an expert in programming language, so if Anyone knows? Can you have a nested private class and define it outside this class in Java? Anyone?
I think you can, because I think that's the way I learned it. It was defined outside. I don't know if it gives you the same level of protection as having it nested, though.
No, in C++, I think you can do that, right? In C++,
Okay.
maybe you can do that. Seems
Okay,
like that.
I could
But
just
I'm
fool around
not
with
sure
it.
about that programming language feature, right?
Okay, all right, no problem. Thank you.
Okay. So next, so let's look at the node, right? Nested private class node. It's very similar to your SLL node, right? So you have the data here, you have the data here, you have the previous pointer, you have the next pointer, right? This is kind of additional information compared with SLL. And you just have the constructor, you initialize everything for the previous pointer, next pointer, and the data or the information of the node. Okay, and then get element, get previous, get next, set previous, set next. Simple, right? We don't need to go over this. Okay, now look at the constructor, doubly linked list. So you have header is equal to node of null, null, null. Trailer is equal to node of null, header, null. Header dot set next is trailer. How does this work? See, when you call the first line header, what happens? The information is null here, and the previous pointer is null, and the next pointer is null, right? This is your header. Okay, next pointer is null. Next, trailer. Trailer creates a new node. Trailer creates a new node. The information is null, and the previous pointer is a header, right? And the next pointer is null. But if you look at this, this is not fixed, right? The next pointer of header should be set to this trailer. That you will fix in line 4. Header dot set next is trailer. So fix this, you get header dot set next is trailer. Got it? So this is the constructor. There are 0 elements in the linked list. Still you have 2 nodes. These are the sentinel nodes, header and trailer. And there is no information, right? So this is your header and this is your trailer. That's it. This is null. Okay. There is no information here. It does not store information. Okay, next, size, return size is empty, simple. First, it's very simple. So what is it? Header dot next dot get data, right? Header does not contain information. It is the node immediately after the header node that has the information. Suppose the list is empty, then you don't have any data, right? Return null. Similarly for trailer, trailer's previous node and get data from it, right? That is the last node or the information in the last node. Okay. Next, so we will look at the unified functions now. So if you understand this is very simple actually. If you understand this, then all the other 4 functions make use of these add between or remove. That's it. Add between. So what is the meaning of this? So you have a predecessor, you have a successor. Suppose they are like this before. You want to create a node with information E such that its predecessor is this, its successor is this. That means you want to add a node in between these 2 nodes. So what do? You create a node, right? Newest is equal to node of E, with the information E, and with the previous node as the predecessor, with the next node as successor. Okay, let me call this as P, let me call this as S, right? This is the newest. Next node as successor. Okay, what about line 5? Predecessor dot set next is newest. See, now these links should be removed. They should be fixed, right? Predecessor dot set next is equal to newest. Successor dot set previous is equal to newest. Right? That's it. So initially there were two links like this. From line 4, you created a node and added two links. And with this, you are fixing two other links. So totally there are 4 links, 2 plus 2. Right? All these 4 links are new, and you kind of removed this previously existing links. Right? That's it. So add a node in between 2 successive nodes or consecutive nodes, and size plus plus. Okay, simple. This is simple, right? Add between. So if you have any questions, please feel free to shoot. Okay. Remove. Why do we have add between here, but we don't have a remove between? Right? We will see. Suppose you have this node, you want to delete. Okay, let me write the predecessor, successor, everything. Okay, so you want to delete this node, remove node, right? Delete this node. But this is not of the form remove between. We don't need it. Why? Because we can always find predecessor and successor given a node. Right? See, this is not just add, this is add between. But we don't have remove between, it's just remove. Given a pointer to a node, you want to directly remove it. But what about fixing the links between its predecessor and successor? We don't need those to input because we can compute it on the fly. See, predecessor is nothing but node dot get previous. If you take the previous pointer of that node, you get the predecessor. If you take the next pointer of that node, you get the successor. That means you can compute it. You don't need these two. Input should be given in the parameters, right? Now what do? Predecessor dot set next is successor. Successor dot set previous is equal to predecessor. That means these links are gone. Make sense?
Professor, in add between, so we're going to do this. I guess we're going to do the searching for the predecessor and successor outside of this method.
Don't worry about it. So assume that you are already given the predecessor and successor. Assume that there is no searching here.
Okay.
See, here, whenever you are given a function, you need to assume that the input is already given to you. You don't need to worry about how is this input computed. Right?
Okay. Okay. Got it. Okay.
So we will make sure this is computed as fast as possible. I mean, not for arbitrary node, but right, we will see. For the 4 functions, this is dead easy. We will see that, right?
Yeah, Professor, but given the case that if you go back to some slides to show the nodes, maybe one more. Sorry, one more.
This one?
Oh, sorry, not this one. The one showing the airports.
Oh, here?
Yeah. So here, if I say I don't know where I want to add, so I just say okay, add something between JFK and San Francisco. Then probably I have to figure out what is the JFK element or the node of JFK, and what is the node? Basically, the pointer of JFK and the pointer of San Francisco, right?
True. You're right. See, if you want to add between two arbitrary successive nodes, then it is true. It is complicated, right? But we are not solving the problem of adding the node between some arbitrary, ith index or something like that. We are just constructing this private function so that we can use it to add at the first position and at the last position. Right? So we will see that, right? We will understand it when we look at how it is used. Okay, now see. After understanding this slide, it will be crystal clear why we defined it that way. Okay, now look at this. Now you understand what is add between and remove function, right? Now look at add first. It is just add between the header node and the next node of the header node. Is this correct? Do you agree with this code?
Yes, that's very clever.
Right? See, because our aim was adding at the first position and adding at the last position. Okay, what about add last? Add between trailer's previous node and trailer. Make sense?
Yes.
See, we are not adding at the ith index, or right? We don't need those functions here. We are just looking at add first and add last. But by defining add between in a unified way, we could just use that private function in a beautiful way. Right? So if there is some problem or changes, we just need to change the add between function, and all these functions will be untouched. Right? Maintainability will be awesome. Right? This is modularity, maintainability, generality, and so on. It will be easier to maintain the code if it is this way. Right? You might say, okay, it is adding one more function, maybe it is slowing down because of function calls. Maybe you can increase the performance, right? If you can repeat some of the sentences again and again, but who cares, right? See, modularity sometimes is more important when you have a code with, say, millions or billions of lines of code. I mean, software with billions of lines of code. Right, so maintainability is more important because of cost, effort, so on. Anyway, now let's come back. We had the remove function. Let's see how we can use that remove function in remove first and remove last. Now look at this. Remove first. Remove the node after the header node. Done. Remove last, remove the node after previous to the trailer node. Okay, we could have implemented a remove as giving the predecessor and successor also, right? Yes, that is true. I mean, we could have, right? We could have done that. I mean, that is true. But we don't need to do it always. I mean, this is also fine, right? But if you want to write it like something like this, remove between, and what do you give here? Header and header, next, right? I mean, you can also do this. That's fine. That's fine. No problem. You can also do this. I mean, there are multiple ways of coding, right? But this is one simple way the authors of this book have implemented. It's a nice way. Make sense?
Yes, thank you.
Okay, so now can you tell me the complexity of all these four functions? These four functions depend on add between and remove. Now let's go to add between and remove. What is the complexity of these two functions? Constant time, constant number of instructions. Each instruction takes constant time. So it's constant time, right? Theta of 1 or O of 1 time complexity. Now let's compare. We haven't covered dynamic arrays yet, right? We will see that later. But it inherits a lot of complexities from static arrays, except the size. The size in static arrays was limited, fixed, but in dynamic arrays, assume that it is unlimited. Unlimited in the sense, as long as you have memory on your computers, you can keep increasing, right? Something like that. Okay, let's see. Insert first position. What about arrays? It takes n time, right? Because all the elements have to be shifted. What about SLL? O of 1, O of 1. Okay, what about insert last? O of 1 here, O of 1 here, and arrays, no problem. Last position. I mean, add 1, right? Insert between, that means you are given predecessor and successor, adjacent to values or nodes or pointers or positions, whatever. You want to insert an item between them. What about dynamic arrays? Right? It is tough. You have to shift all the elements, only then you can insert, right? So it's O of n. What about SLL? I mean, you can also define insert between. Not a problem. It's easily doable. DLL. Insert at a particular index. Suppose I say you want to insert an element and that should have the index of 100. That means that should be the 100th element in that data structure. What about arrays? You need to shift everything. What about SLL? Right, that depends on the index. You need to move to that index, right? Index can be n, so it can be O of n time, right? Worst case, right? What about DLL? Same thing. Insert at 1 trillion position.
Professor.
Yes.
So here for the single or circular or double linked, so they don't have the index, right? So you have to
scan
traverse to.
Exactly.
You have to scan. Okay, I see.
Right, you have to scan them. I mean, what is the 100th node? You need to scan it. Right? So you cannot directly go to the 100th node, but in arrays, you can go to directly at the 100th node, but you cannot, I mean, you can edit the position at the 100th node, but you cannot insert a value there, a new value there. So that's why we have modify at indexes of 1. But adding the new value at index, I mean, creating and adding, right? That's not possible in O of 1, right? You need to shift all the elements. Okay, what about delete first? Easy, easy. Arrays, no, shift.
You have to move everything.
Delete last, easy. What about SLL? No. DLL, easy.
Don't
right?
know where's the last.
Okay, what about deleted index?
Correct.
Deleted index
That's
is
the same as insert index.
complicated everywhere, right? Okay, what about access at index? Easy for arrays. Access at index, modify at index is easy. But deleting at index or inserting at index for arrays, it's difficult. Make sense? So you need to understand each and every operation here and the complexity associated with it. Okay, so all the complexities are derived from arrays itself. Then what is dynamic here? Dynamic comes in the size, right? Static arrays, the size is fixed, limited. But in dynamic arrays, you can keep on adding elements even after you hit the capacity. You go beyond the capacity. not capacity of your computers, but the capacity that you have initially defined, right? We will see all that later. And this is not just O of 1. I mean, you need to say amortized O of 1. And we will see what is that amortized complexity and all later. Okay. So I have a question for you. So suppose we worked on a project. That project required a particular problem to be solved. I mean, we had to use a particular data structure. Okay, so the constraints are like this. That data structure required these two operations to be implemented. Okay, rotate function and remove function. Rotate function, okay, you want to rotate and remove the node you are currently at. We had to implement these two operations efficiently, and we needed a data structure. Can you tell me, how do you design a data structure to solve these operations efficiently?
Would you pick a CLL because that's the easiest way to rotate?
CLL, easiest way to rotate. Rotate function is good, but what about remove at a particular node or a particular?
The same delete at index.
Right, but how can you remove?
You rotate till the ideal element that you want to remove to the first, then you do the delete first.
Okay, repeat again. Rotate and then
you rotate to the ideal element that you want to remove to the first place, then you delete it first.
Okay, good. That solves the problem. But what about complexity? Complexity is still O of n for remove. That's not efficient implementation. Rotate is O of 1, I agree. But remove, both your ideas are taking O of n time. Though you can implement it, it's not unimplementable.
No, if you use SLL or CLL, the delete first is O1.
For remove operation, no, it's not O of 1. Remove operation, right? How do you remove operation? I'll think about this.
It's the same as delete at index, I think, because you have to identify which one to remove to that class.
Right. So suppose you have identified that. How do you delete it?
I think what the suggestion was look at the first object in a CLL and keep rotating until the object you want to delete is at first. Then you're just deleting first, which is O of 1. I think that's what
I
he was trying to
see. Okay, I understand. But you still okay, remove that particular operation is O of 1, but you are applying that
rotation is n.
O of n times, right?
That's right. You
are
rotate
applying
it
that function
n times.
Is it possible to do both in O of 1, even scanning in O of 1? See, even going to that position, right? So here you are calling rotate multiple times. Can you do everything efficiently?
That's a good question.
See, currently it is like this, O of n. See, even if you're given the pointer, think about it.
Yeah,
I give you the pointer. So look at this. Suppose this is your CLL. I give you this pointer. I want to delete this. How do you delete this?
Oh, that's probably not too hard. You just reorganize the head and the tail.
Right, and that's what
but
I'm
you still
saying.
have to, you still have
Yeah.
to traverse, you still have to traverse to get there.
No,
Right.
but the person said you know what to delete, right?
No. So what I'm saying is, see, solving the problem is not tough. Solving the problem is dead easy. But solving the problem efficiently is the question. Solving is not even the question. Solving it efficiently, we want to do everything in one time. Right? Okay, so here I will give you the answer because we can proceed to more ideas, right? We need to come up with slightly different data structure, which is an amalgamation of the ideas covered here. We need to create something called circularly doubly linked list.
Okay.
Make sense? What we have studied here is just circularly singly linked list. Suppose you had circularly doubly linked list. Right? You can also define it that way, right? Makes sense?
CDLL.
Right. You can say CSLL here, CDLL here.
Yeah.
Now think about it. Rotate is still of one time. And delete is what? You know the predecessor, you know the successor. Delete is at a node is of one. Does that make sense?
Yeah.
Yes, so delete at index would now be O of 1, you're saying, not O of n, right?
Yes, of one. But if you use a circularly doubly linked list, because now you can easily find the predecessor. Once you have the predecessor and successor, you can easily delete that node, right? No need to scan, nothing. Make sense?
Yeah.
Professor, how do you find the predecessor and the successor in O of 1? Does the remove function give you the node, or it gives you an index or the
No.
value?
So the question is, as we defined earlier, right? Remove code is something like this. Remove at a particular node. We are already given this node. You just want to implement.
Okay, I see.
Alright.
I see.
Right? You're already
see.
given the node. You want to implement the remove function for that node. So you just take node predecessor and node's successor and change the pointers here and there. Done.
Yeah.
Make sense? So does this make sense?
Yes.
Yeah.
So see, though we have covered all the essentials, right? But we did not cover circularly DLL separately. But you should be able to come up with ideas like this, right? It might be amalgamation of two tiny data structures to create something new based on whatever has been asked. Based on the operations, maybe you need to combine multiple data structures, right? Sometimes I have seen one problem which required the amalgamation of 4 or 5 data structures. You use a hash table, so each points to a tree, that points to something else, right? I mean, it can be a very complicated, but if you understand the basics of all data structures, right? You know, you have to use rotate function. Rotate is awesome in CLL. You know, you have to use remove function. Remove is excellent in DLL. Why don't we combine both CLL and DLL? So CDLL, right? So identify for every operation what is the best data structure, right? And then try to, you know, combine them in some possible way, in a good way, so that you get the best of both the worlds, right? Fine. Now let's move to next topic. So this is a very, very important table. See, just using, say, lists or something like that in Python or Java, is not enough. You should be able to know exactly what each line of code takes, right? The complexity analysis, right? So though the function call is same, so it might be function. Suppose you have an object.a function, object.b function, just 2 lines, right? But you should know what this operation is. This operation takes O of 1 time. This operation takes O of n time. This operation takes O of log n time, right? So it's not just about coding, right? The analysis part of it is also important. Okay, next, let's move to list. What is the difference between ADT and a data structure? Before we go to list, right? Let's think about the difference between ADT and data structures. So did we discuss this before? What is ADT and what is a data structure?
An ADT can be implemented, different ADTs can be implemented using different data structures.
You can see the same ADT can be implemented using different data structures. Good, right? So this means abstract data type, right? Abstract data type. And you know, this is data structures, right? Okay. So ADT are like interfaces in Java, right? So interface, what is an interface? And you can say data structures are like classes or methods and so on. Classes with methods and many other data types and so on. What is an interface? I mean, it might be called with a new keyword in Python, right? I think it might have a different name in C++, but we will focus on Java. So what is an interface in Java? So interface is a collection of method names or function names. Function names, right? Suppose you have an interface and then you have function names like A, B, C, that's it. But no implementation, right? Only function names without implementation. So what are these? Implementation of these functions. Okay, so why do we focus on just function names if we are not giving implementation details? So it is something like this. So it's like a standard, right? Standard. For example, stack, queue, right? DQ, and all these can be ADTs. And even list can be an ADT. So it says you need to have a structure where you have a function call called set and a function call called get, right? Something like that. How you implement set and get, it is up to you. Different programming languages or different compilers or different packages might implement these functions in different ways. It's their headache, right? But the standard says you need to have these function names, right? They should take these parameters or something like that, right? These parameters with these data types or something like that, and implement them as per your programming language, compiler, a package, whatever, right? So this does not care for the implementation. This cares for what are the operations. Tell me more about the operations. Give a list of operations that it has to handle. And why you can think of this as a standard, right? Whoever implements this, I mean, it is up to them to implement it, but whoever implements this should have those operations. For example, push operation in stack, pop operation in stack, right? So in the stack ADT, you call, you define all those function names, and you don't care how it is implemented. You can use an array, you can use a linked list, doesn't matter, just implement it, right? So those are the data structures, whatever we discussed now, right? Array is a data structure, list, linked list is a data structure, SLL, CLL, DLL, and later we will see dynamic arrays, right? All these are data structures. And stack, queue, DQ, trees, right? Hash tables. All these can be ADTs. Some programming languages also implement them as data structure or something, but assume that they are all ADTs. They expose a collection of functions. Tree, it should have insert, it should have delete, it should have search. Majorly these three operations. How you implement it, it's your headache. Stack, it should have push, it should have pop. Queue, it should have push, it should have pop. DQ, it should have insert first, insert last, delete first, delete last. Hash table, right? It should have insert and search or contain, something like that, right? It just gives a couple of functions. It does not say how to implement it. And most of these can be implemented using arrays, or they can be implemented using linked lists, or they can be implemented using linked node representation, right? Something like this. And you can also have graphs and all that here. And how do you implement it? Graphs can be implemented using matrices, or graphs can be implemented using array of linked lists, right? Or it can be more complicated also. Make sense? These are ADTs. So list ADT, that means it just exposes a couple of functions, and then we will see the data structure that implements it in the best possible way. Okay. So list ADT. Size, these are the methods, okay? Size is empty, get of I give you the index I, you give me the element at index I, right? Set of I comma E, I give you the index as well as the element, you set the value at index I with element E. Okay, so similarly, add of I comma E. What's the difference between set and add? Here, this is just modification at the ith element, but here it is insertion of a new element at the ith position. Then remove of I. So you want to delete the element at the ith position. Now think about it. So these are just the methods or functions. And I'm saying that this is an ADT. That means the implementations of all these functions is not given. What do you mean by I? What do you mean by index I? Should it be an array? No. You could have chosen a linked list to implement this list, right? Get of I, if you use array, it is very easy. Get of I, if you use a singly linked list, it is complicated. That means it is slow. You need to scan that position, right? So depending on which data structure you use, the complexities vary. Make sense? So here, our focus is on arrays, right? Later, we will see the array implementation of this list called array list. Okay, so before that, let's understand this, the set of functions more rigorously. Add of 0, comma a. I mean, we are just having all these operations, right? Add of 0, comma a. Return value is nothing, right? Whenever you have a method, return value is nothing here. And contents at the 0th index, you have a. Add 0b. B will be added to the 0th index. A shifts. Get of 1. At 1 you have a. A will be returned. Set 2, comma c. What about 2 position? Set means what? Modify, right? What do you have here at 2 positions? 0, 1, 2. The list does not contain 2 position here. I mean, modification, right? So hence you are getting an error. Similarly, add 2c. Add is fine. Setting is modification. It was not existing. Adding means you create an entry and add it, right? So on. And you can follow all these operations, right? See, whenever we said list, right, did we say how it is implemented? No. The methods are these, the return values are these, the list content should be like this. Whether you use array or list, it depends on the package, it depends on the programming language, right? So on. Now, look at the interface here. Interface. Whenever you see interface, you need to think this is an ADT. So it has these basic variables. Of course, the functions act on variables, right? If there are no variables, what will the functions act on? And then you have methods. Get, int. So it also shows the data type of all these input, output, and everything. Okay. Next, E is kind of template, right, for arbitrary data type. So something like that. Okay. Next, it also shows what exceptions will be output, index out of bounds, and right, something like this. Right. Get, set, add, remove. That's the 4 functions we saw earlier. And how you implement this? You can use arrays or you can use linked list, but just implement this, right? It does not give the implementation. It is just exposing the functions. We'll see the array implementation. Now look at, suppose you use array to implement this, right? And this is the most common implementation of list. Whenever you see the implementations in programming language, right, list, they are using array list, right? They are majorly using array lists. Okay, now look at this. Get and set methods are fast, but add and remove methods are slow. Why is it? Get of I, accessing index super fast. Set at I, setting at an index super fast. But add, adding at an index, removing at an index, as you have already seen in our first scoreboard application, right? It requires a lot of shifts. Adding at ith position requires the shift of all these elements. Deleting at the ith position requires you to shift all these elements 1 step to the left, right? So in the worst case, it is n. So O of n time for add and remove, but O of 1 time for get and set, right? But nothing else we can do. These are the only data structures we have, either list or arrays. If we have suppose we have lists, then get and set. So it depends also on accessing. Whenever you set I, you need to access it. Accessing it itself, right? Scanning takes a lot of time. So you cannot get away with O of n, right? You will have O of n somewhere. You cannot have O of 1 in everything. Now, let's look at the array list implementation. So array list implements list, right? This is an interface. Whenever you are implementing an interface, so you need to use this implements keyword. So this data structure, right? Array list implements, or this class implements the list interface. That means whatever functions you defined in list, right, should be expressed, should be defined in array list. See, all the functions we wrote there, right? Those will be expanded here. Those will be given definitions here. Okay. Now, you can also, introduce new functions. You can introduce as many new functions as possible. You can also introduce new variables and information data. That's fine, totally fine. Okay, let's define capacity. Initial capacity is 16, but this defines the capacity of the array. Okay. Next, you have the array itself, and then you have the size. You know, the number of elements in the array, right, is size. Then what about capacity? Capacity is the maximum limit that the array can extend to. What if it goes beyond this? Then we will see. We will do a resize, right? As we discussed, we are implementing dynamic arrays here. Then we will resize whenever required. See, this is the resize function. Okay, now let's see. Array list, this capacity is you are creating an array here. Size simple, is empty, get, set, add, remove. We will see these functions. These are easy functions, right? We have already seen some of the codes for this. Add, remove, and all. We saw them in the scoreboard application. It's very similar, not a big deal. Check index. You want to check whether whatever you are working with, the index, is it belongs to one of the legal indices or not. If it is illegal, right? If the array is only of size 10, but you are calling something, let's say 1 millionth position, right? It's illegal index, then you throw exception. Resize, we will see resize later. Get, see, whenever you deal with indices, right, always do check index. Check index if the index is legal or not, right? Then return date of I here. Setting, again, setting is very simple. So I will skip a lot of these codes. And add. Currently, do not look at lines 5 and 6. We will come to this later. Check index, and then use the logic we discussed in the scoreboard application, right? That's your add function. Yes.
So line 4 does not have a return. So if the index is not in range, you throw some
exception. Right.
Exception. Okay.
Right. See, there are two ways to encounter, right, problems. So like whenever you encounter problems, two ways to deal with those problems. So one is throwing exceptions and stopping them, right? Stopping the entire program, terminating the program. But that's not a good idea. I mean, in how many softwares, whenever you give some incorrect things, the software stops or terminates? It doesn't, right? You need to catch exceptions and handle them very well. Or sometimes you don't throw exceptions at all. You just handle every type of other values and all, and ask for re-entering a correct size again, right? There are many ways of handling all these problems. One is never throwing an exception. right? And having some looping logic to get a proper value. So another is throwing exception and termination. That's a very bad idea. Another good way is throwing exception, but catching it and trying to resolve it, right? Maybe you can say, I'm using, it was illegal, I'm using this as the index. So are you comfortable with it? I mean, something like that. Or asking again the customer to give a proper legal value. So if a customer gives 1 million, or you can say, maybe you meant the last position here, the last index is here, something like that, right? Handling exception. But here, I mean, for simplicity, we will throw and terminate, right? Doesn't matter. Okay, the logic here, right? From 7 to 10, you need to shift all the data points, make data and add it there, right? Make space and add the new data item here. What about remove function? Remove function is very similar. We already have seen the logic of this also, right? In the scoreboard application, very similar, very similar. So that is the core component of your array list. But what we don't know are lines 5 and 6. If size is equal to data.length, what if the number of elements, right, is same as the capacity? That means if you add one more item, what happens then? Overflow problem, right? You will not have enough space in your array. Hence, you have to resize. Hence, you have to resize. There is no space. You have to resize. Okay, we will try to understand this concept. Okay, and
Professor,
amortized analysis. Yes.
So here, resize a system function, or it's just defined in this data method?
A resize is defined in this class. We will see the code of it.
In this class. Oh, okay.
Check index. See, if the index is out of bounds, throw an exception. And look at the resize function. Resize the capacity. So what are we doing here? So this is the new capacity, right? We are creating an array. And we are copying all the elements from the previous array to the new array, right? We are copying all the elements from the previous array to the new array. We are making sure that the previous array name, array reference, array pointer points to the new array. That's your resize function.
Professor, what about the data, the original data? The garbage collection will handle it?
Right. You don't need to worry about the original data because the garbage collector will collect it later. Right? So let's see a different way to see this. And see, the problem we are dealing with is whenever you add an element and there is not enough space, that leads to the overflow problem. And the good way to solve that problem is by growing the array. You need to increase the size of the array. But you cannot increase the size of the same static array, right? Because it is static. I mean, you can only create that space once. You cannot increase it here. That's not possible in static arrays. So we create another static array of double the size, 2 times the size, 2 times the size. If the size is X, this is 2X, 2 times the size. And then copy all these elements to the new array. Right? Copy all these elements. And now make sure A points to this new array. A points to this new array. That means you lost the only pointer reference to the old array, you don't need to worry about it. That will be garbage collected. Right? So here is the logic. Grow array. Allocate a new array with larger capacity. Right? This is the larger capacity. Typically, we do 2 times.
And there's no limit you could do, right? You could
no,
do 3
we
times.
will see the analysis. We will see the analysis.
Okay.
Right?
Okay.
And copy all these elements from the A array, old array, to the new array, B array. And then set the pointer of the old array to the new array. That means we lost the pointer to the old array contents, right? That old array contents will be garbage collected later. You don't need to worry about it. Okay, so this is the logic behind resize function. So dynamic array doesn't mean we can, it can dynamically increase it. That's not the logic behind it, right? Dynamic array means we create another bigger static array and copy all these elements, right? And then we have many more elements here. That we can add, double the size, right? So we can add a lot more elements. So we don't need to resize until this is completely full. Once this is completely full, again, we create another array, double the size of this, and copy all these things here, and A points to this, and this will be garbage collected. This keeps repeating. Repeat this process. Okay. Now, there is a lot of theory behind this. We will understand it one by one. So here is your resize function, the add function with the resize, right? Now you understand why we have those 2 lines, what it means, but we still don't know the analysis of resize function. Now, here is a diagram. Suppose your initial capacity is 2. This is the capacity, right? This is the capacity. And assume that all these numbers tell you the number of elements in the array, right? That means you are, suppose you keep adding 1 element at a time, the number of elements keeps increasing, 8, 9, 10, so on. And what happens to time? Suppose our initial capacity is 2. Or say 1. Let's say 1. You add an element, right? The size is equal to data length, so it will double, right? You are doubling the size. Or you can say, like, when you are increasing the number of elements to 2, right? You have to double the size. You double the size of the array. Size in the sense capacity of the array. Now this took 2 time units, right? This is the number of primitive operations. You can assume comparison operations or copy operations, whatever, right? Comparison or copy operation or whatever. Comparison would be better because that is so that takes a lot of time, right? Comparison. Okay. So it doubled. And you're fine for 2 elements, right? Next, you add the 3rd element, you add the 4th element. Again, it should double. Now you're fine for next 4 elements. Then you are doubling the array. Next, you're fine for next 8 elements, right? Totally 16 elements, and then you're doubling the array. But if you look at it, whenever you are doubling, you are, the time taken to copy all these elements, here it is 8. Here it is 4. Here it is 2. Here it is 16. Make sense? No. Is it 16 or is it 1?
I think it's half. It's just half. Oh, but if we increase from 8 to 16, you copy 8.
Right. You copy 8, but total is 16, right?
Yes.
Right. I mean, you can think of 8 or 16. It doesn't matter. I mean, for computation, it doesn't matter. It's kind of the same. We'll see the analysis, right? See, we said adding an element takes O of n time, right? What about this resize? How much time does it take, the resize function?
O of n.
Is it O of n?
Well, yeah, if you're copying over
It is.
from
Okay.
one to the other, you're copying over n.
It's a little bit more than that.
Good. So resize takes a lot of time. Okay. Suppose you're doing this. Add last. Suppose you're just adding an element at the last position in an array list, right? Ideally, this should take O of 1 time. Make sense? Right?
Yeah.
Again, add last. It should take O of 1 time. Correct? Add last. This should take O of 1 time. And so on, ideally. But at some point, when you add last, it will call a resize function. Correct?
Yeah.
So that add last will take O of n time. So you can also think of this graph as the add last function, right? This took O of 1 time, 1 time, 1 time. This took 2 time, right? 4 time units, 8 time units, 16 time units, so on. Now you want to find what is the complexity of this add last. How do you solve it? You can say if, right, size is equal to power of 2, right, then add last takes O of n time, right? If size is not power of 2, then it takes O of 1 time. This is good. I mean, you can say something like this using a condition. But typically, we don't use this condition. Right? We don't use these conditions. We will just say O of 1 amortized. And why do we say that? Now let's think about it. So what is the meaning of amortized analysis? So that means, let me erase these. That means, on an average, what is the number of operations it takes whenever you add last? This is not the average case complexity. Think about it. Average case complexity assumes all possible data distribution, right? And considers the average based on probability and everything. This is not based on data distribution. Are we caring for the value of these add last? No, we are not caring for the value. We are not caring for the data distribution. The time taken is more whenever the number of elements is of the power, 2 power something, right? So power of 2. So that's why we are facing this problem, right? Okay, so how do we solve this problem? The average, see, it is something like this: 1 plus 2 plus 1 plus 4 plus 1 plus 1 plus 1 plus 8 plus, right? If you do this, say up till 16, 1 plus 1 plus. Divided by how many elements are there? 16. It will be of, let's say,
This will be 2.
Let's say something like this. N, I will say N, and do this up till N. You will see that this is O of N time.
Professor,
sorry,
I think they should be 2. Yeah, of 1. Yeah. When N goes to infinity, the limit is 2.
The numerator will be O of 1. So if you add all these things, right? See, that means you can break this up into a couple of pieces and add all these pieces to the next one. I mean, you can add this piece here, you can add this piece here, you can add this piece here, right?
All right.
So on. And remove this entire line. So you can cut these into pieces and add that piece here, piece here. So on an average, you will see that the number of operations, right, for add last, I mean, we will call it as O of 1 amortized. So it is the average of all these operations. I mean, we don't write it as a conditional, right? When it is a power of 2, it is this. When it is not a power of 2, it is O of 1. But we will try to consider the average of this, and that is called amortized analysis. And here the amortized analysis of dynamic arrays for add last is O of 1. Make sense? So does this make sense? So if you look at this plot, suppose you are resizing not in a geometric progression, but in an arithmetic progression. So what is the meaning of this? Arithmetic progression. So if size is equal to, suppose, length, right, or capacity, then resize length, what is it, say plus 3. This is an arithmetic progression, right? This is not a geometric. We are not doing multiplied by 2. We are adding a constant, not multiplying by a constant. So this is an arithmetic progression. If we do an arithmetic progression, you will see that the amortized case analysis, amortized complexity will be O of n for add last. So hence, we should not resize the size by, I mean, in arithmetic progression, right? We should always do it in geometric progression, right? Okay, so why do we need this amortized analysis? Because, see, one operation might be slow here, right? One of these add last is taking a lot of time. But suppose you are doing all these operations in a sequence, add last, add last, add last, add last, add last, right? If you're doing it in a sequence, one takes 1 time, some of them take 1 time, some of them take, 4 time, 1, 1, 1, 1, then 8 time, and so on. It doesn't matter whether this operation took 8 or 4 and all. On an average, each of these operations takes of 1 time, right? That's the idea behind it. Performing a sequence of operations is efficient, right? That's the meaning of amortized analysis. So instead of considering the worst case time is n, right? But that happens very rarely, right? So hence we are getting O of 1. Yeah, use geometric progression, do not use arithmetic progression. And now the question is, why did we multiply by 2? What if we multiply by 10? What happens if we multiply by 10? What happens if we multiply by 0.01? It doesn't make sense. You're not increasing the size, you're decreasing the size, right? 0.01 doesn't make sense. So R has to be greater than 1. What if you choose 10 times? Good. For a long time, you don't need to resize. That's the beauty of it. But what is the flaw? You used a lot of space. So there is a trade-off between runtime and memory usage. Instead of multiplying, resizing by two times, if you do 10 times, of course, the runtime efficiency, right? The average runtime will be lower, much lower, but you're using more space. I mean, we don't know whether the application really needs 10 times, right? So what if you use R is equal to 1.001? I mean, that's fine. But very quickly, you will need to resize again, right? The memory usage is better, but very quickly, you will have to resize again. So it's a trade-off between runtime and memory, right? Time and space. So you need to choose wisely. Typically, practically, we use R is equal to 2. Next. Shrinking. Okay. Suppose we are increasing, we are facing this problem. What if the array is being shrunken, right? Like, what happens then? That means you are deleting the elements. Remove last. Suppose you are doing remove last. At some point, the number of elements will be so tiny compared with the capacity of the array. You don't need all that extra space. What do you need to do? You can again resize, but this time resize to a smaller value, not to a larger value, to a smaller value. Again, copy all those elements. You can save space. As you know, space is important, right? But, okay, like what if you say, if it is less than half, right? If the number of elements is less than half the capacity, I will, reduce it down to this. Shrink the array to this. You can do that. That's fine. You can do that. But the problem is, what if you keep doing this? See, the number of elements you add last, you need to double, resize and double, and remove last. Now it satisfies this condition, and you shrink again. So if you keep doing this repeatedly, you will be resizing. That means doubling and then shrinking by a factor of 2 in a to and fro motion. That takes up a lot of time. So instead of 1 by 2, what typically we do is we keep it as 1 by 4th, so that there is no this to and fro motion between resizing to doubling the size and shrinking the size again and again and again, right? Oscillation between growing and shrinking. And all the concepts are very similar. Shrinking the dynamic array can also be done if the number of elements is less than 1/4 of the capacity. And why did we do 1/4? Again, because of geometric series, right? Never go for arithmetic series. And why didn't we do 1 by 2? Because of oscillation, to avoid this oscillation problem. I mean, we could have selected 1 by 8 also, 1 by 6 also. That's fine. It doesn't matter. But practically this is used, right? So here is one more idea, right? Look at these two codes. Both have a single for loop, but the left side code's running time is theta n squared. The right side code's running time is theta n. Why are they different? Why are they different? See, coding is not just about, typing some code, right? It's much deeper. Programming is much deeper. It requires algorithm analysis. What is a string? You need to think about the basics. String is a static array. A string builder is a dynamic array. Right? So whenever you do this, answer is equal to answer plus C, it is resizing every time. Every time. If it resizes every time, what happens? The complexity blows up, right? The runtime is n squared. So here sp.append, what is the difference between this and this? Append is adding one more character, right? Adding one more character. You don't need to resize it for adding every character. For half of the times, you don't need to resize, right? Once it hits a power of 2, then you resize. So only a few number of times. And we saw earlier using amortized analysis. If you consider the sequence of operations, this is the meaning. The sequence of operations, you will see that on an average, right, adding one character is like taking theta one time. So adding n characters is like taking theta n time. Right? Very similar code, one for loop, but one runs in theta n squared, one runs in theta of n time. Right? Hence, the knowledge about data structures, analysis of algorithms, all these are important. Okay, positional list is not in the topic, right? But I will just give you one application. So think about text editor. If you want to implement a text editor, you have a cursor here, right? You add characters at the point of the cursor and you delete characters at the point of the cursor. Which data structure do you want to use? Do you want to use an array? No. So we create an ADT called positional list. And the best way to implement that is using a doubly linked list. And if you have a doubly linked list, I mean, think about this pointer in your text editor, any text editor you use, right? When you keep adding characters, what happens? It's like pointing to a node and you are adding nodes, more nodes at that position or after that position. And when you delete characters in a text editor, it's like deleting characters, right? Just before or after that particular node. All these are of one time, right? Adding one character or deleting one character at a specific position, at the cursor point, right? So the beauty of this, what if you had implemented a text editor as an array? It's gone, right? The time complexity will be horrible, right? So this is the beauty of understanding about data structures and algorithms. Okay, so we will stop here. I will not cover this, but for more information, you can scan all these slides, right? Positional list, it's implemented using doubly linked list. Okay, we'll stop here.